Welcome back to this course on C programming and assembly language. We were in module 1. In the last lecture, we concluded by discussing about a particular instruction called the SCAS byte, right? We did SCAS B word or D word, and what this basically did was to compare either AL, AX or EAX with the contents pointed to by DI, and we also looked at a prefix to this instruction which is called REPNE, repeat until repeat as long as it is not equal, right? And we will continue this lecture with some more in such similar instructions. So in this lecture we will look at the following instruction, which is a compare operation. Compare operation on a string. So let us assume that in my memory I have two different arrays, one sitting in my extra segment, okay. This is my extra segment and this is my data segment. And let us assume that there are a bunch of bytes here, okay, n bytes, and out here as well. So these are n bytes and so are these. Now my job is to write a program to find out if these two arrays have the same data, which means that all the locations have to have exactly the same value. So if I had to do this in regular assembly programming, then I would have to loop through each location, find out if each location matches or mismatches, and then increment the address and so on. It is possible to do this kind of a comparison in a single shot because the x86 architecture supports string instructions. So there is an instruction called CMPS byte, word or D word, right? So CMPS B would compare a byte, CMPS W would compare a word, and CMPS D would compare a D word. So what does this do? It basically compares the contents of the source index with the contents of destination index, and because it is a compare instruction, it is only going to affect the flag, it will not affect either the SI location or the DI location, right. So which means only flag is affected. So just like the SCASB, right, the scan byte, after executing this instruction, the source index and the destination index will either be auto incremented or auto decremented. So it is SI plus minus 1, 2 or 4, and this plus or minus is determined by the direction flag, right. So similarly DI will become DI plus minus 1/, 2/4 depending on whether we are accessing a word, a byte, a word or a D word in memory. So let us now proceed and let's assume that in this example n is let's say this is about 100 bytes. Okay. So what I want to do is to now write a program where I can compare location by location and say if the entire array matches or stop at the first mismatch, right. So just like the SCASB, I am going to go ahead and first clear the direction flag, right. So what does this do? It basically clears direction flag implies auto increment. Auto increment of SI/DI. Okay. So then let us also assume in the previous page that the first location of both arrays is given by ADDR underscore 2 and this is ADDR underscore 1. So starting at ADDR 1, I am now comparing 100 locations with another array starting at ADDR 2 and going through another 100 locations in the extra segment. Okay. So obviously I need to move these addresses into my source index and destination index appropriately. Move SI comma 1 and move DI comma ADDR underscore 2. So just like we have been mentioning that the segment address and the offset of the register SI or DI gives the full address, the source index is always controlled by the data segment register, this is the full address, and the destination index is controlled by the extra segment. Okay. Now let me move my count into the register, right, which is 100. Note that this is in decimal, not in hexadecimal now. Okay. And I will add this instruction which is CMPS B. Right, this is basically load the address. This is load another address. So this is init counter, right. So when I do a compare CMPS B, it is going to compare contents of SI, right, with contents of DI and then auto increment SI plus 1 and DI will be DI plus 1. Just like we had in the SCASB instruction, this does it only for one location, and if I want to repeat this till all the 100 locations have been scanned, I need to add a prefix to it, and that prefix now is as long as the two locations are equal, you keep going, right. So you keep PE, right. So you keep going either until as long as both the compare compare operation results in equal values, or the ECX eventually goes down to 0. So now because of my prefix, ECX will become ECX minus 1 after each of these operations. So, by the end when we finish this instruction REPE CMPSB and then proceed to the next instruction, it would have compared all the locations that are the same, and at the first mismatch it would have stopped, or it would have, or when you are done with all the 100 locations, it means that all the locations match exactly, right. So, if instead of a byte, if I wanted to compare it with a word, then I would have to do CMPSW, in which case my SI and DI would auto increment by a value of 2, and if I wanted to compare it with a D word, then I would do CMPSD, and the SI and DI would auto increment by a value of 4 each time. So, similar to this, there is another instruction which is known as a move instruction, right, data movement instruction. Data movement instruction, right, but string or an array, right. So, in this case the example we are dealing with is, you have a memory block which is sitting in my data segment, right, data segment, this is my extra segment, and I have n locations which are starting at ADDR underscore 1, and or this time I could call it a source address. Source address in my data segment, and let us assume that this is some n bytes, and I have another location in my extra segment which is called DEST underscore ADDR, and what I want to do is to copy these n bytes from this to this, which implies from my data segment I want to copy all the n bytes, right. It could be the 100 bytes as an example, right, or 256 bytes from my data segment SRC underscore address offset to extra segment destination underscore ADDR offset, and 100 locations thereon, right. So, how would you do this? It turns out that there is an instruction called moves byte, right, and as with every string instruction, moves word or moves the word, right. And so, let us go ahead and try to write the simple program for this. If I want to execute this, I would do CLD, which is basically auto increment DI and SI. Then I would move my source index with SRC underscore ADDR. Then I would move my destination index with destination underscore ADDR, and then of course I have to load my count. So, I would move ECX comma n, whatever the value of n is, right, and then I will do moves byte. Okay. So, what does this moves byte do? It will simply copy to the destination index the contents of source index, right, and of course this is going to be ES colon destination index, and this is data segment colon source index, right. And because this is a move operation and it is not an ALU operation, obviously a flag will not be set. So, therefore, you cannot use any kind of flag condition to decide if you want to repeat or you want to stop this operation, right. So remember that REPE would go on as long as they are equal, REPNE would go on as long as they are not equal, and so on. But here, because no flag is going to be set, I cannot use any of those conditions, and therefore I am simply going to put an unconditional prefix, just REP, which means repeat this moves byte operation until ECX has reached 0, right. So, and yeah, by the way, after doing the moves byte, the destination index will get plus minus 1 2 or 4, and so will the source index. Okay. So here when I do this REP moves byte, it means that destination index will get contents of source index, right, and then DI will be DI plus 1, SI will also be SI plus 1, and ECX, let me just, ECX will be auto decremented. So, in summary, we have studied 3 different string instructions: SCASB, which is scan a string for a particular pattern which can be loaded in AL, AX or EAX; CMPSB or CMPSWD, whatever, can be used to compare the contents of SI and DI, right, and you can use a prefix of REPE to repeat this operation as long as they are equal. In the SCASB case, we repeated as long as they were not equal, and then the third operation is a data movement operation from the source index in the data segment to the destination index in the extra segment, as long as my ECX is not 0.